Let's talk about an engineering puzzle that's at the heart of pretty much all the tech we use. How do you prove a design is actually going to work before you spend the time and money to build it? We're going to dive into how engineers try to model reality and, well, the surprising places where that model can fall apart. So let's kick things off with a little question for you. What could your phone, your car, and a satellite whipping around the Earth possibly have in common? I mean, they're wildly different technologies, right? But deep down, there's one thing that they all absolutely positively need to function. And that's it. Perfectly stable power. Without it, your phone is just a fancy paperweight. Your car is dead in the driveway, and that multi-billion-dollar satellite, yeah, that's just space junk. It's this silent, invisible system that's the foundation for everything. Okay, so let's pull back the curtain on this critical component, because even though you probably never think about it, getting it wrong can have some pretty spectacular consequences. You know, this quote from the source paper just hits the nail on the head. A great power supply is totally invisible. It just works. But a bad one? Ooh, it makes its presence known. And trust me, not in a good way. So, the hero of our story today, or maybe the villain depending on the design, is the switched mode power supply, or SMPS for short. Now, this isn't your simple little wall charger. This is a super complex, high-efficiency circuit that has to take whatever power's coming in and convert it with just incredible precision. It is literally the beating heart of almost every modern gadget you own. Designing one of these things is a huge challenge, so let's meet the three different kinds of detectives, or, the three main approaches that engineers use to crack this case. And this is the million-dollar question, right? You can't just slap together a dozen power supplies for a new satellite and, hope for the best. You have to know with a really high degree of certainty that your design is solid before a single part is ordered. So how on earth do they do that? First up, you've got the analyst. This approach is all about pure hardcore mathematics. The analyst uses these incredibly complex models to write out the equations that should, in theory, predict exactly how the circuit will behave. It's all about creating a perfect prediction on paper. Then you have the simulator. This engineer basically builds a digital twin of the circuit inside a computer. They can then run thousands of tests on this virtual version, pushing it to its limits, all without ever touching a real component. It's an incredibly powerful way to see what might happen. And last but not least, we have the experimentalist. This is the get your hands dirty approach. They build a real physical prototype and hook it up to some seriously sophisticated lab equipment. Their job isn't to predict what will happen, but to measure what is happening. This is our ground truth. So you've got these three very different ways to get to the truth, and each one has its pros and cons. The math is super fast, but it's based on approximations. The simulation is incredibly detailed, but hey, it's only as accurate as the virtual model you build. And the experiment, well, that gives you the real deal answer, but it takes a lot of time and costs a lot of money. The whole game is balancing these trade-offs. All right, we've met our three investigators. Now it's time to put their findings side by side and see what story the evidence tells us. And here it is, the initial evidence. This graph shows how the power supply responds to different frequencies. And, at first glance, it looks like a slam dunk. All the lines, the predictions from the math in the simulation, and the solid line from the real-world test, they're all right on top of each other. Looks like case closed, right? I mean, the paper itself says it pretty plainly. The plots are almost identical. It really looks like all three approaches came to the exact same conclusion. But here's the thing. In engineering, the word almost can be a very, very dangerous thing. This is where the real detective work begins. We have to look past the obvious agreement and start hunting for the tiny flaws, the cracks in the story. And you find those clues hiding in the error plots. This is where we see just how much the models are straying from reality. And suddenly, things don't look so perfect anymore. As the frequency gets higher, you can see the models, especially their predictions for a critical factor called phase, start to drift away from what was actually measured. And that leads us to this magic number, about 1/10. The researchers figured out that the models, both the math and the simulation, were only really reliable up to about 1/10 of the circuit's main operating frequency. Once you go past that point, you're in uncharted territory where the map no longer matches the terrain. And this is where the stories really split apart. The pure math model, it was the most optimistic. It predicted the most stable design. The simulation was a little more cautious. But here's the kicker, the real surprise. the actual physical hardware was even more stable than any of the models predicted. In this case, reality actually turned out to be better than the theory. So, after looking at all the evidence, after seeing where the stories line up and where they fall apart, what's the final verdict here? Well, the verdict is pretty clear. You need all three tools in your toolbox. The math is great for getting started, the simulation is for deep dives, and the experiment is for the final, real-world confirmation. No single model is perfect, and you have to know its limits. And maybe the best part? Sometimes the real world has some pretty nice surprises in store for you. And this is what it all comes down to. It's not just numbers on a page or lines of code. It's a real workbench with real hardware, scopes, and wires. This is the place where all that theory finally comes face to face with reality. But the investigation had one last twist in store. The coolest result wasn't just that the real circuit was more stable, it was how it was more stable. The measurement showed it was actually becoming safer from instability at higher frequencies, something that none of the models even hinted at. So the experiment didn't just check the theories, it uncovered a brand new mystery. And that kind of leaves us with a bigger question, doesn't it? We build our entire modern world on these incredible models and simulations. But if even for a circuit like this, our best tools can't quite capture the full picture, what other fascinating little mysteries are still hiding in our electronics, just waiting for the right experiment to bring them into the light?